Okay. Hey. Say something. I'm doing a sound check.
Test one,
Thank you.
2.
Okay. Yeah. Oop, doop, doop, doop. All right. Now I'm playing catch up for a second.
Howdy.
What's up?
I said howdy.
Yeah.
Hi. Howdy.
Yeehaw.
Oh, I tried. Okay. Gotcha. I'm sorting out my new people here. Oh, there's another one. Here is another one.
Hey, Matt.
Yeah, right. Just a second here. Hi.
I saw Matt posted a article on what was that, out of order
Go in here.
memory barriers, memory models.
Oh, I think I've caught up, more or less.
Matt, you can
Hi.
throw a link in the chat for this article.
Oh, that's interesting. Not quite caught up yet, but I'm getting there. Thought I'd caught up and then more here. Okay, so now I'm going to claim caught up enough. Yeah, so this is Coffee Compiler Club. You're being videotaped. If you don't like being videotaped, bail out now and watch it on Twitter later. Oh, I got somebody else. Okay, fine. Here's Arthur. And, you know, this is all about compilers and language runtimes and typing systems and concurrency and garbage collection and anything and everything to do with language implementation and runtimes. It's an open mic. I reserve the right to moderate, never had to do it. I don't have a set agenda. We roll about. I sometimes start with a brief summary of where I'm at with AA, but we usually pivot into, I don't know what, somebody has something and we go somewhere. And you know, that's the starting spiel. I'll do my AA update because been beating on it hard this last couple of weeks. It's trying to merge forward flow typing and Hindley-Milner typing. I hit here's another person. I hit a sort of a hard block earlier this week, and I'm trying to sort my way through it. And that's the way I was combining the two frameworks was to do treat them both as instances of monotone analysis frameworks. You can go Google that if you want to see what they are, but they're pretty straightforward. Constant propagation is a canonical example of a monotone analysis framework, but a lot of other things are monotone analysis frameworks as well. And to do a combination, well, in a monotone analysis framework, there's these things called transfer functions, which are basically the abstract interpretation of like add of something and a 0 gives you the something back, or add of 2 and 3 gives you 5. So the transfer functions are just take two instances from your input lattice, you get an instance from the output lattice. They have to be monotonic. When you're combining these frameworks, you end up with transfer functions that take types from, say, Hindley-Milner and also types from standard constant propagation and get you back out a constant propagation or a Hindley-Milner type. And when you get these crossing transfer functions, you have an opportunity that the combined algorithm is strictly stronger than running either of the two independent algorithms any number of times to fixed points. So that's where I've been headed at. And what I bunked my head on was the obvious interpretation of Hindley-Milner typing and what you would do with it to improve constant propagation types turns out to be a not monotonic. And that because it's not monotonic, then you blow the monotonicity requirements for your monotone analysis framework. And typically it means that you can find a test case for which you can show there is no principal type. That is, there's multiple equivalently good types, but no one is better than the other, and no one dominates. I'm unable to produce that example either, which tells me that I'm probably doing something wrong. So I fought for a while, coming up with some interesting examples for which, you know, you would scratch your head and say, I don't know how this would type, or it types, but it has something, or it shouldn't type, but it can some of the times or not, whatever. But I never came up with a clear-cut canonical, this is a busted example where you don't get a principal type. Which tells me I'm doing something wrong, and that's where I'm at. That's my last week and a half's been at. So heavy into the type theory side of things, and a whole lot of math and logics. If you want to see an example, actually I can throw one in the chat now because I beat a bunch of good looking examples out. And then you can stare at it for a second and say, no, I don't want to go there. Here is, where's my poster child example? That's this is probably the better looking one. So here's a poster child in chat. It's running an infinite loop, which you can ignore, pretend there's another breakout in there. The question is it typeable at all? The key point here is the middle line where I say, what's this type? I'm merging an identity function and a function which ignores its input and returns a float. If you have to combine them in standard Hindley-Milner, say the if of whatever your predicate is combines them, then the return value for float fun is actually float arrow float, which you then pass a string in the following line, you can't type it. So you get a type error. Okay, you can't pass a string in for a float. Now, if you run the code, you would see that, and this is where forward flow typing does it. He would come along and say, well, the value for name is set to def. It's a non-empty string. So I'm going to take X arrow float, not the identity call, and I don't have to do the unification. So I only do one of the two unifications there on the arm of the if that's taken. Well, now I have a function that ignores its string argument, returns me a float. Then I do a float to string, which never returns me an empty string. It always returns me some kind of string. And I loop, and I call name with another different non-empty string. I hit a fixed point, I'm done, and the thing's typeable. So that's a case where I can use forward flow typing to improve a Hindley-Milner type and make a program typeable that's not otherwise typeable. But this doesn't actually help me get better types in forward flow typing. So it doesn't improve the reverse direction. That just means that I would run the constant propagation first, followed by Hindley-Milner, and I'd get the best type out. So that's a sample of the kind of shit I've been doing. But now if I go the reverse direction, life gets ugly. I don't want to go there right now unless if people want to go there, I'll go there. It's really deep, really quick. I can probably step you through. I don't have prepared slides or anything, so it'll just be, you know, me talking and throwing in chat. Whatever. Otherwise, we can pivot to something more sensible. Like,
but what I was wondering about, does this have some correspondence with refinement types when we have some predicates for the types? Because I believe it might be possible to type this expression with refinement typing as well.
It might type with like ML sub. I don't know what you mean by refinement types because I don't have the jargon in my head for that particular jargon word. No,
I will look something.
yeah, throw a link in chat. I probably have seen the concept. I don't know that particular name for it. So this one has the property that they replace the identity call with an arbitrarily complicated function, and the second guy with an arbitrarily complicated function. And I'm using a flow type to tell me to not unify these two arbitrarily complicated expressions. And because I don't unify them, I get a better answer out. That's the story with that one. Whereas okay, this is oh, it's not a is this a dependent types?
Well, almost. I'm not sure what is the exact relationship between refinement types and dependent types. They are not the same.
Okay, fine.
They're close, but they're different in their
And then
mechanics.
have subtyping. So yeah, I think this will type with ML sub, which does a subtyping thing, I think. I'm not positive. I'd have to go sort it through as an example. There are some things ML sub does that Hindley-Milner doesn't. That's the obvious thing. There are things that forward flow typing I can do that I can't get any other way because I get a lot more precision of the typings where it works. And where it typically fails is that in a forward flow system, you take types at function calls and you merge all their input types. And that approximation immediately loses too much information. And when you're done and you leave the function, you have lost it because the approximation and what you return is an heavily approximated value. Whereas in Hindley-Milner, at the return point, you immediately relift the output types to be equal to one of the input types according to the typing relationship. The output type depends on the input type. And that would be how I would improve forward flow typing in general, is to say your output type in a forward flow system is equivalent to one of the input types based on whatever Hindley-Milner declares. And the failure with that one is I get non-monotonic pretty quick, which means I can run into a system that I have, like it never stabilizes or there's no.
Are we trying to calculate the output type of the function entirely, or are we trying to calculate the output type of the function at a particular call site?
For this particular
example, are we
example,
essentially treating every single call site as an independent sort of single assignment thing?
At this particular example, I want to get a type for every point, or show that it can't be typed. Like Hindley-Milner won't type this, leading in with a GCP declaring is empty to be always true or always false, doing some dead code elimination, and then running Hindley-Milner will type it, right? So there's
but you don't expect the constant propagation to be so aggressive as to replace the entire function call with like return to string 1.2.
Oh, it could. It absolutely could. When I do typing, if the type turns into some constant like 1.2, how do I spell a type of float function? Well, it's typed as float arrow float in Hindley-Milner. So there's two different types of float function. And it, right, so one of them gets this type, which is what Hindley-Milner declares, because he unifies identity and ignore your input, return a float. Whereas forward flow typing says, oh, throw away the identity guy. It's this type, which is the type of a free type variable. This is the Hindley-Milner type after forward flow typing is done with it. So this is a Hindley-Milner type after forward flow is done with it. Forward flow typing is easy for me to just take a more precise value and have a 1.2 instead of float, which then propagates through float string, and I actually get a string of 1.2 is exactly what you were saying there, Aaron. I'd say, yeah, you're 1.2. The string 1.2, it's all good.
ML sub will type this too in simple sub.
Do you have an instance of ML sub up and running?
No, right now, but I believe it will type it as the result type will be at least float. The lower bound will be at least float, and not the.
Okay, now you're very quiet. I can't hear you.
I believe that can you hear me now?
Yeah, it's better.
Okay. I believe the result type can be typed by ML sub, and simple sub, and will be at least float. The lower bound will be at least float, because when you try to unify the alpha with float, and that will be, I believe that would end up the lower bound will be at least float. That would mean.
Okay, but it's passed a string.
This
is why I don't actually. I don't know, but I don't think ML sub gets this example.
It will type it, but when you try to use it, it will give error. It will give an error when the loop def, when you try to use it. It will type the definition but when you try to use the function, it will say then that it can unify the string.
All right, Cole, I can't read it. Look like you put a piece of paper up to the camera.
Sorry, just idly fidgeting with stuff on my desk.
Oh, okay, fine. He had big font, and it was like you're trying to hold a sign up, and I was like, "What? Nah, fine."
Sorry.
Okay, so I'll agree to disagree that I don't think ML sub will get this, and I'd love to see the ML sub running, and I probably should set it up. And there's some web page I think that'll run it. And
I can try it. I can try.
Be cool, because I was curious to see what type he gives. If he gives a looser type for the input that says I take a string or a float, I always return a float, that would work. Except on the identity call, you return a string or a float. You take a string or a float, return a string or a float. Then it's not typed, in my opinion. That's a runtime type error, and we were looking for static typing. SML. Oh, SML. Oh, that's SML. I don't think SML types this either, but it's an online one. I'd have to rewrite this in ML code, Cameron. That's a good example. I don't have an ML parser in my head. I can't.
I don't know ML sub, so.
Oh, is there an ML? That's ML of New Jersey. Does that have? I don't think it does. No. It's standard ML. It's not doing. Oh, there's the one I'm looking for. Or that's the GitHub repo. Is that going to execute?
Yeah, it's the page.
Oh, it will execute. Okay, so you have to rewrite it in simple sub.
Yeah.
Yeah. Okay, fine. So anyhow, I can make the examples arbitrarily complicated on what forward flow uses to recognize a value and what two things get unified. And the question isn't, can this one per se? I'm looking for sort of the simplest example that cannot be done with ML sub. Because I'm certain that there's an example that can't, because I'm going to throw down arbitrary crap out of, constant propagation can get arbitrarily deep. It's a different story. And then I still don't have a thing that goes in the reverse direction, which is the what I got stuck on. And I'm off doing another attempt at going in the reverse direction with a different strategy.
What gives you the intuition that you can go in the reverse direction? Is this the type that you got? Okay, hang on. I want to read your type though. I mean, you're not going to like it because you don't like OR in types.
No, I don't like OR because that OR requires you to have a runtime test. In my opinion, it's statically typed means I don't have to have a dynamic test for what the value is. Here, I have to have a dynamic test, but it's only one of the two. It's only int or float, so you're guaranteed that your test always produces one of the two things. So when you do the thing like you apply float fun to an ABC, you'll get one of these two answers back. And when you go float to string, presumably he has to also test the result type. Like we didn't ask what is the type of result. This is the type of the overall expression, but what is the type of result? Because see how many runtime tests you need, but presumably you can add the runtime test. And I'm trying to say, no, there's no runtime. There's a reason I don't like OR. There's no runtime test. So I'll grant you that he will be typable with an OR. Why do I think I can do the reverse direction? Because because every time I type these things, I get a flow type at a point and I get a Hindley-Milner type at every point. And the two types are structurally very similar. But after a function call, Hindley-Milner has a stronger structural type than the flow. The flow guy has approximated sort of massively. And then what I can do is walk the Hindley-Milner's input types and the flow input types structurally together, one, in parallel. They're two different typing systems, but they have wherever you have a record, you have a record, you have a function, that they're all structurally the same. You can walk them. Wherever the output mentions a type, a Hindley-Milner output type mentions an input type, you can get the corresponding flow type from the inputs. So the canonical example is a map call from, map of A to B. The map is typed as a function from A to B and a collection of A's, and returns B back in a collection of B's. So that's the Hindley-Milner easy type. Somewhere in the world, I call map with a function of float to string and an array of floats. And I've called map in 10 different places. And so the flow type is approximated a function from anything to anything, taking a collection of anything, turn a collection of anything. He reports back, all types from map are a collection of anything. Same as an object array in Java. But in the Hindley-Milner knows it's a fucking string array you got back, because the B type is a string, because the input type of float string is float arrow string. And so you match the output type to the input type, and the corresponding one is string on the flow side. So you get a string array out on the flow side. So then you can lift the flow output to be a string array, and now proceed forward constant propagation with a string array instead of an object array. So there's an obvious way to improve these things. That's what my intuition is telling me. And when I come down to doing it in practice, I get a non-monotonic result as soon as I go from a Hindley-Milner type, which doesn't have any exciting structure, to one that has repeated types. Because the flow guide, because these are all monotonic, if you ever decide that you don't have structure, you can never have structure again. So somewhere in the world, I've seen a function that looks like A arrow B, and then later during the course of the Hindley-Milner algorithm, it tightens up to being A arrow A, becomes the identity function. Where the first A arrow B is used, I can't say the input is related to the output, and so the output falls in flow types. Later, the input says, no, you're equal to your output, or your output's equal to your input. Well, I know something about the input, so I know something about the output and the flow types. Now it lifts. Well, that's not monotonic. It went from a weaker type to a stronger type. Suddenly, I don't have monotonicity, and I lose the key property.
So you're basically having to reschedule anywhere that you had A's and B's.
No, as soon as
So
you
that you
lose
can unify them?
monotonicity, you can loop forever in these algorithms. They don't terminate. If you stop them arbitrarily, because they this waffle back and forth between. So as soon as I lift the type, I get a sharper type out of the flow type. He goes to an if statement. Because he has a sharper type, he declares one branch of the if dead. Because one branch is dead, he doesn't have to unify. Because he doesn't have to unify, you're back to an A or B. Because you're back to an A or B, you can't lift. You fall from an int to a scalar. Because you're a scalar, you can't use the if test to crush one of the two arms, and you're cycling. So that's the reason you have to have monotonicity. Once you've ever made the decision that a flow type is not int, it fell below an int or above, whichever way your top or bottom are, you're dead. I mean, you can't ever go back. And the problem I have here is when Hindley-Milner, I arbitrarily.
So your problem is you had code that restricted the possibilities in such a way that you now knew that the code was dead that was restricting the possibilities, so that code comes back.
Yeah.
Okay, because it was a constraint that was in the code that became dead that told you that that code was dead.
Yeah. So
Okay,
in other monotone analysis framework situations where I have a non-monotonic function, I can usually produce a counterexample where it's blatantly obvious that there's no least common fixed point and the algorithm would waffle back and forth. The reason it's waffling is because it's looking for a fixed point, there isn't one, and it's going back and forth between two.
It's the classic, this statement is false.
Yes.
Once I assume that it's true, it tells me that it's false, but then it's false, so I can't use it, so I must assume that it's true, and yeah.
Yep. That's exactly what's going on. In the land of C2 in Hotspot, when this wasn't all understood so theoretically so nicely. These mistakes are made all the time. And the usual story is eventually you proved false is equal to true, and you in the optimizer, then immediately ate the entire program up and says the entire program is false. And you got a broken compilation much later. It's very suck. You got a giant theorem prover. As soon as he proves this false is equal to true, you're dead.
Wait. This kind of thing can happen in dead code, and that makes sense to like eliminate everything because, well, you've proved that it cannot happen, so it's dead code.
C2 is full of places where I say, I suspect this code, I'm proving false is true. Let me assume this code is dead and just stall. Don't do anything. And a little while later, the dead code eliminator cleans it out and you're fine. So there is a funny property that C2 has where everywhere he would produce a conflict, a direct conflict in like proving false is true, he simply stalls. And a lot of these cases show up where I say, this thing is an identity function on this thing, and you're infinitely replacing it with itself. And so I have a lot of these tests that say, oh, your identity on yourself, that's usually like an add of 0 and yourself. Well, that's an identity of yourself, which is an add of 0 on yourself. And you're like, how do you have an add that has a tight loop on itself without a phi function? You have a looping thing without a phi. Okay, the phi died, the loop died. The loop was a cutoff of a thing, and now it's an infinite loop that can't be reached. These are really common. So there's a lot of these things that say, oh, you got an unreachable, you basically have an unreachable infinite loop. I'll just stall, not do anything, and eventually the dead code eliminator will throw it out, and it's all fine.
So yeah, but why is it problematic? These situations where you see a conflict, I assume that you see a conflict, it's dead code. Like you can do whatever because it will be either eliminated or will never be executed.
The problem here is that the code is not dead, and I don't see a conflict. Instead, I see a series of steps that are all independently sensible to take, one after another. They just turn out to be looping on yourself. And the loop can be arbitrarily long. I can't look for this loop per se, although if I looked for it, all I would do is report, hey, you're not monotonic somewhere.
Ah, okay. So it's that your transformations are not monotonic, and it's possible to loop them. If it's possible, well, it will happen one.
Right. So the original C2 had a lot of places where you weren't monotonic that eventually we got beaten out. The other aspect of that was you got these cut off, these dead loops that appeared to be not monotonic, or you had to handle them still monotonically, but you also wanted to stop trying to make progress on them because they were stupid and dead. And so you had to look for the cutoff there. In the AA implementation, working with, I strongly test for monotonicity at every small step. So I just hit it right away.
Does it make sense to do something like clone the function and be like, okay, there's going to be one version of this function that takes an int, one version of this function that takes a string, and one version of this function that takes a type dynamic. And if I know that it's an int, I stick in the int one. And if I know that it's a string, I stick in the string one. And if I can't prove it, I stick in the type dynamic one. And now it just is 3 different functions that have 3 different types.
Right.
And each of those would type more strongly.
Right. So this is not solving the problem, but it is also something that I'm likely to do anyhow. So the reason to do it anyhow is that I would like to have generic types that will allow primitives, but have the performance of having a primitive where you're using a primitive. And so I want to have internal clones that are specialized for each of the different primitives. So the hash table,
preferably polynomially many clones.
Yeah. Yes. This is an issue. So in the not theoretically worked out AA side of things, I do have ambiguous functions that represent, for instance, int to int or float to float or string to string as an ambiguous choice to be decided upon later. These things can all get decided upon. Currently in all my examples, I get decided upon at each individual use site. But if you look at like the function for add, it is given to you as a single function that you would pass around. It appears to have the behavior that it's either int to int arrow int, or it's float float arrow float, or string string arrow string. But at each individual use case, I know I can specialize it to just the one. But if you say, give me the primitive add as a function and pass it around, I'll pass around an ambiguous function pointer that has to be specializable at each point. And at the moment, I don't need a runtime test to do that specialization. I'll have a typing time thing. But add as a primitive, you can ask for it, and it's an ambiguous type. And the general situation there is I have this class of ambiguous functions. So actually, just overloads. I have a class of an overloaded function. And you ask for it, and it gives you a single function pointer. You can check it for identity. It's equivalent to itself or hashes or whatever. It does all the right properties. It's a single function pointer. And every individual context where you would call it, I can resolve the overload and go to a particular chunk of code that's specialized for those type arguments.
That was sort of my question. Are you also going to generate a function that dispatches dynamically at runtime?
Yeah, at the moment, I don't need to dispatch those dynamically. That's what I'm saying.
Because you have no type dynamic.
Because I don't need a type dynamic. Or I have a type dynamic, except at each use site, it's known to be not dynamic. So I'll pass it around as a dynamic function type up until you're going to apply it. And at that application site, I'll know. That's the theory. I don't know that's going to work out in practice. I don't have a counterexample. I don't have a theory that says it's correct either.
So if I have a function that's like paint.
Yeah.
And I've got a whole bunch of paintables that exist in my world that's like, it's got an X and a Y and a height and a width and some kind of buffer that I'm moving to the screen. And those are all different types and potentially causing different functions. And
yeah, I'm not attempting to solve this for what I would call overloaded, like single inheritance virtual calls. This was for me doing this for primitives.
So far, Cliff has said that it's as polymorphic as you want, as long as you can figure it out at compile time.
Yes. No, but that's legit. And if I say primitives only, then I can even get more restrictive yet and say, well, it's polymorphic for the count of the 5 different primitives I'm going to support, and when we're done.
Yeah. No, it's very important that when you're designing, like everything has to fit together as a whole, right? So you have a picture of exactly what this is going to be.
Yeah.
Right. So.
Yeah. It's
but that's fair to say we're polymorphic over the structs, and if you used a class, you get what you asked for, and that's going to be slow. Deal.
There's a cost model I want people to be aware of or be able to rely on, and one of the cost models is if I call plus on 2 ints, it's a fucking quarter clock cycle x86 add, right? No matter what your context. So if you pass that plus around as an arbitrary function in and out of a hash table that maps blahs to functions, and you pull a random function pointer out and you call it in a context, you better get your expected cost model, right? If you do a virtual call, you kind of expect a cost model to be that of a virtual call, which is going to be a jump register indirect on an x86. It has some costs to it, and that's a different cost.
But
yeah, I like virtual calls, but it's better if they don't surprise you.
Yeah, that's the point. There's no surprises on the cost model. That's what I want to have there.
So what I was wondering about, you mentioned that you're passing around these ambiguous function pointers in a sense. So I was wondering if it is possible to leak this abstraction. For example, getting 2 different concrete pointers out of that overloaded function set and compare them as not equal, like getting the float exactly. And the integer. Yeah.
And the answer is no, or I haven't done it right and I shouldn't bother. So the answer is no, because there is only one concrete function pointer, but at the point at where you apply it, I'll be able to pull out in constant time the exact one you meant and inline it on the spot. So should be able to resolve it statically at every point, knock on plastic. And if I can't, then I'll probably blow a different error at you. So that's an AA design philosophy, which says the cost model is understood and obvious. And if you want syntactic sugar that has a cost, you can get it. And that might mean that your plus call in a weird context becomes a virtual call and has an overhead. But you've asked for it because you said, please, sir, make my life easier and allow syntactic sugar here. And then there's a performance version which says, plus is never expensive. And therefore, if I can't resolve it at compile time, you get a type error. It says, hey, you have an ambiguous function call to plus here. I don't know which the plus you means. This won't be cheap. Are you sure you want to go here? Whatever. It's a type error. Fix it or admit that you're allowing yourself to be, bad here.
But I don't have to fix that for the whole program.
You don't have to fix the whole program. No. These are regional. These would be These would be scoped annotations. Like the default scope would be syntactic sugar, please make my life easy for everybody. Somewhere in the middle, I said, and this loop is hot. And I declare the loop being typed as fast, which means the cost model changes. If I can't guarantee a low cost model, you'll throw a type error. And then buried inside of that, I'd say, and here I actually do want to be expensive and, you know, all right, fine.
If I try and call from fast code to slow code, the compiler
Yeah,
like,
I
yeah,
have to
no.
annotate and say, and here I'm going to call slow code, and that's okay. And I just scope it, but you have to excuse the exceptions every time. That's my theory on how to make the language give you a cost model that is understandable and tolerable.
Right. So I can be like, hey, this is my hot monitoring loop that's going through a lot of data.
Right.
And then I say, oh, I actually won the Bitcoin, find the hash that's important. Turn off all the performance stuff. Now we're going to go like actually declare victory.
Yeah, go call
That can be
complicated,
slow.
weird shit because I won the race. Yes, yes. So I have one of these financial analysis tools. It walks through these terabyte log files, pulls out all the products. Well, there's 1,000, every 1,000 transactions, there's a new product, maybe not in random, statistically speaking. So if I look at 1 billion transactions, I get 1 million new products out. But most of the time I get the same product. And so I want to do a hash lookup on each of the products. If I miss in the hash table, I found a new product. Now I'm going to do slow, do some weird shit and initialize the new product and shove in the hash table. If I hit in the hash table, I still want to be fast because that's the 1,000x more common situation. And I want that code to remain fast. So I want it to complain at me if I accidentally do an allocation or do anything, you know, stupid there. When I find an existing product, and I'm just going to do some more statistical analysis on the existing, whatever, fine. So there's plenty of examples I have for where you want this fast, slow dichotomy, and that's that piece. So I have a theory on overloaded. So I'm backing outward from questions to prior topics. So I have a theory on doing overloaded functions that I can efficiently and unambiguously make calls to.
And those annotations live in the typing lattice?
Yeah, more or less, yeah. So the theory is I'll let you add a new annotation to an existing function, a new overload to an existing function, if I can tile the tree-like space of your arguments such that you have no ambiguous conflicts with the prior overloads. So you can add a new add that does matrix to matrix addition, for instance, because it doesn't conflict with string to string or int to int. But two different guys couldn't come through. And you could do add to matrix and matrix to add, and all things as long as they don't conflict, so that I have an unambiguous resolution and I can do it from the locally observable types and blah, blah, blah. That's the theory on that guy. And yeah, they live in the type system. Like I said, I have a more complicated type system than maybe beats the. But this is all with forward flow typing. Like you can go to town on forward flow typing, or at least I figured out how to go to town on forward flow typing. It's just like crazy.
I pointed out that ML sub will.
All right, TDR, you're not hearable again, not audible.
Yeah, now?
Better. I don't know what's going on there.
Okay. I will boost the microphone, maybe.
It's like your mic is really quiet.
Yeah.
And why
Now,
does Zoom doesn't have, like Discord has per person volume controls that for the host.
The Chrome has it. It will adjust the volume based when it decides it, and it's.
I cannot hear you.
Oh, no.
All right, I lost your video. Now I lost your sound.
Now, yeah, do you hear now?
Yeah, it's better.
Something happened. I don't know. I pointed out that the ML set will still not type it because I missed the function to float to string.
Oh, yeah, we had the discussion the other day. If float to string requires you to have a float and gives you back a string out, then you're stuck.
Yeah,
Float to string takes a scalar. And if it's not a float, it gives something stupid back.
Yeah.
But otherwise, it always gives you a non-empty string in all cases.
It won't, the ML will still won't able to type it because we have to unify the float with string, and that will not happen.
Yeah, that was the point of that operation.
Yeah. Because
Okay.
I miss it. I miss it. Yeah. Cool.
Yeah.
I did wonder a little bit about things like that with people are so used to these defensive programmings that the defensive patterns are going to leave you with this, like, I take a scalar and return something that makes sense, or an error, and your types end up getting much wider just because everything can take anything and can give back an error.
Yeah, I don't like the things that take an arbitrary, except for toString. I don't like for debugging. I don't like things that take an arbitrary argument and do something with it. But there are a few cases like hash table should take a hashable, I guess, which requires you to have a hash code and an equality test. So maybe that's not the same thing. Yeah, I don't know. Things that take arbitrary scalars and do something with them. There's not a lot of them that make sense except copy. You can copy an arbitrary scalar about.
Aaron, do you mean that embedding more information in the types? In like an example, the type you're passing in has to be a positive integer. Do you mean this, or?
That's not.
Yeah, what I was thinking about was often at the interface to some library, people are being very defensive, and they're like, if you give me a null pointer, or you give me a thing that's sized too big or sized too small or broken in any number of ways, I'm going to give you back an error message that's like, you gave me garbage.
Yeah.
But now something that's trying to detect the types of the system are like, I take a pointer that might be null and I don't know what the size of the thing is. And the assertions all went away because they became runtime tests.
Yeah.
And you sort of have to convince the developers to stop doing those tests at runtime so the compiler can do them at compile time so that it can be helpful.
Yeah, and that style of defensiveness also comes from, from a different time in software as well, when you were when a library was typically in a global space getting hammered on by, so if you screwed up a library,
by C code had good reasons for being that defensive.
Right. Well, you could screw up some other running application that had nothing to do with you, just because you happen to be using the same library. I'm talking
that got fixed a long time ago.
It got fixed a long time ago, but all of us at the time were reading Petzold and what was the other one? Defensive programming or what,
Yeah, right.
We were all reading the same books.
I don't think that's the issue here. I think that I think having a library return a result type, like Ellen would call a result, an option type that says you're an okay and here's a result, or you're an error and here's what the hell. Like what is the right place and time to do exception throws versus doing returning a tagged union with a result or an error? Right. In the land of Java, you get these exceptions that have a pretty horrific issue that they crawl through spaces and don't let people clean up invariants unless they catch arbitrary exceptions, and then just rethrow arbitrary exceptions, and you type exceptions that everyone ignores the type and blah, blah, blah. And when you go to like a module boundary where you're expecting separate compilation, I'm kind of the opinion I don't want to have exceptions come out of the modules even anyway. Module returns a tag thing, so that you're not getting exceptions when you call out to some other module. You're getting back a thing that you have to check in case the module hates what you handed it. But how do you want to, what do people think on this one? What's the right way to handle interfaces to separate compilation units? Within my own compilation unit, I get a lot more freedom. Within a separate compilation unit, I'm pulling a Maven fucking library. What is it? What's the right interface for that library to say, I don't like you, I'm going to explode now?
I like the result type that is either an error or an okay, because I can stuff it across a network, whereas I've never had a good understanding of what should happen when I try to throw an exception to another process that's running on another computer.
Right. You serialize it and you throw a string across it and you deserialize it. I did this with H2O. I serialized the fuckers and threw them across and deserialized them and rethrew.
Right. But at that point, you've turned a exception into a result that you then sent across the network and turned back into an exception on the other side.
That's perfectly reasonable. That's perfectly reasonable. I don't see.
But
Exceptions
Even
aren't magic. They're exceptions are ints. I mean, the exceptions are voids. They're as magical
Usually-
as anything else.
I mean, they're long jumps. That's kind of magical.
Well, long jumps certainly were magical when they first appeared.
I don't
but-
want to. Yeah, I'm not certain I want to do long jumps here. But an exception is certainly. I'm sorry. When I say exception, I usually think I get a stack trace back, and the stack trace is terribly useful for debugging things,
I believe
and can be terribly misused in the land of Java. They are frequently terribly misused.
Yeah, I believe exception should be exceptional.
Exactly.
Exactly,
Yeah.
but Java never tried to optimize the stack trace stuff. I mean, there are a billion optimizations that they could do for that.
That's not the performance. People will catch the exception, log something. They can't repair their own state. They can't repair the state of what they got. They'll just catch it and rethrow it as runtime exception because they don't want to deal with annotation of checked exceptions. And after you get 3 or 4 of these things, you get a stack trace which has been inverted every 5th line because it says, and this was caused by this exception, which was caused by. Half the exception handlers internally are broken because they're never tested and they throw exceptions themselves. And so you start with an exception and you get caught in the exception handler and you throw it. I totally debugged this shit. And the 99% solution here is you threw away all the exception handlers and you just took the raw exception out to the top and suddenly it was obvious what was going on. Nor did you need to log because the guy who was logging had no repair opportunity. Since he's not repairing, what the fuck is he even bother reporting? He's dead anyhow. So just get the hell out, all the way out to somebody who could have a chance to repair. And that's typically
that's how exceptions are supposed to work, the way you just described it. You know,
Yes.
don't try catching it unless you're the one that's killing something.
Yes, and you know, and one of the theories I have on AA that I haven't gotten around to is to say if I'm going to throw an exception, you are not allowed to catch and rethrow. You can only catch and repair. So if you can't repair, you can't catch.
But catch and rethrow is fine. It's the catch and wrap that sucks.
See, I would claim if you, but there is a one that says, and I included that model, which was I don't actually catch. Instead, I'm allowed to do a one-off repair, and then the
Right,
same exception
finally.
keeps propagating. So I can do a local corrective action that I know isn't the complete corrective action, and keep going.
But in case of rethrows, I know that in most of the cases this is not what's happening, but in some cases someone could genuinely add more useful context when it is wrapping the exception in another object.
I hear you. And in my experience here is those are both extremely rare and very little more information that you won't get out of just the straight up stack trace.
But the other problem is that you catch the most generic exception and all thing falls apart. You cannot.
Well, right. So people are claiming, yes, that I'm kidding. I don't know what I'm getting out of this library. I'm getting some pile of exceptions. I'll catch them all.
Yeah, catch exception or throwable in Scala, and all the exceptions died of it because you catch them. You should catch only the specific exceptions to your meaning type, a number exception or something like that, not the throwable, not the most generic type.
Right, but that's not how it's used in practice.
I think
That's because a lot of times people don't know what to do with the exception that they're getting. Hey, I get an LDEP not resolved exception out of this call. Fuck, what am I going to do with an LDEP not resolved? Well, but I have to catch something, you know,
Yeah,
because it's
but
an
if you
IO
can-
exception.
But if you can catch the exception because you know it's coming and you can respond to it, then it's not an exception. If you can
Yeah.
repair it, it's not a fucking exception.
Yeah.
Yeah, this is an error. That's why Haskell distinguishes them. One is the exception and the other is an error type.
Well, when you say exception in the Haskell sense, are you saying like I see in other languages,
Haskell
panic?
cannot throw.
This-
Haskell cannot throw. It's some kind of framework to distinguish what is exceptional and what is an error. And there is some discussion when to shoot one. In
Okay, but they have
Haskell,
two
you
different
cannot throw.
flavors. And the exception is catchable still. If it's not catchable, then I would rename it to panic. I'm going to
Yeah,
give you a
in-
stack
in
trace
Ha-
all the way out and kill the process. And you don't
In
get any
Haskell, you cannot.
process.
Yeah,
goes down.
you cannot throw exception in Haskell. They're more like conceptually what one should be exception and the other should be an error. In our case, the most of the error should be errors, not exceptions, because exceptions should be exceptional.
But it didn't make sense. I didn't understand what you're trying to say there.
I will try to find the link and we'll post it. That particular discussion, what should be an error and what is considered an exception.
Yeah, panics are real issues that can't be handled. Yes, and there are like web servers doing top level incoming HTML requests in the land of Java and garbage collection can frequently throw away a broken web request and recover and carry on usefully. The thread dies, the locks it was holding get unwound, there's a bunch of garbage that happened, but presumably it didn't break your caches or leave anything in a broken state, and the web server carries on despite having some kind of hard fault, and it's really expected to catch and handle an exception. I'm not claiming that's a good model, but I claim Java's trying hard to make that work and mostly succeeds. Whereas a lot of errors
doesn't really
are just
catch and handle it. It catches and terminates that.
Yes, that's the
that
handling.
logical context.
Yes, that's the handling. In the land of ecstasy, I would say I killed that container because the container was flawed. And I'll try again later, should I get another request or whatever. You have some reasonable response. The Java reasonable response, I don't care, reasonable, is unlock all lockables and let the garbage collector pick the mess out. And if you broke something in the middle, it remained broken.
Right, but the unlock all lockables happens because it automatically catches it at each lock level and automatically rethrows it. That's the so if you say synchronize this, for example.
Yeah, that's not what actually happened. There's a
well, I understand you wrote the compiler that produces the native code. I'm talking the bytecode. You're right. Yeah, okay.
Yeah, there's no catch even at the bytecode level. And
yes,
unlock.
there is. Yes, there is. There's the
finally an unlock.
Yes, monitor exit is the bytecode. Monitor enter is the bytecode. So if monitor enter finally try final. Well, find. There's no such thing as finally. It's catch all.
The exception unwind path in the interpreter unlocks as it goes, and never you mind finallys or not.
So
apparently you throw exceptions in Haskell.
If I have a throwable that I'm pretty sure is going to be caught, I don't have to actually build the stack trace until such time as it's like, oh, this actually wasn't caught. I'm now going to have to go build the stack trace.
Technically, you don't have to build the stack trace because they're so repetitive that all you have to do is pass a number back, and then it looks that up, and it's set of stack traces that it's built already.
So the place where I've seen people get into trouble with results are, I have a thing that returns a result. The next thing that called it reads it, says, oh, this was an error, wrap that in a result and pass it up. Oh, this was an error, wrap that in a result and pass it up. And now you have this linked list of results that are like error, 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 error. And you had to do work to build all those things. And then you get to the top and it throws it all away because it actually knows how to handle the error.
Right. And I would claim that that's some combination of misuse by the programmer and not language support to help you deal. Because an obvious solution for that one is I have a very short syntactic form which says take the thing back. If it's an error, return immediately with the result that it is, and just let it propagate up without wrapping.
Right. But if it turns out that no one can handle that and it makes it to the top, what I want isn't just, here's an error that we weren't able to deal with, stick it in the database so someone can triage it later. I actually want something that looks like a stack trace that says, here's the error, which came from, which came from, which came from, which came from.
Okay, so the difference between what I would call an exception and what I call an error is do you get a stack trace or not. And C2, by the way, will optimize away stack traces in certain contexts. So that it is doable in some contexts in Java right now. But ignoring that one, do you want an exception with a stack trace every time? I guess, Cameron, your solution is make stack traces cheap, then provide them every time.
I would go even farther there. I would say no stack traces by default.
Oh my God, they're so fucking handy.
It depends on your error model. So in my my language, they cannot bubble up implicitly. So you have to handle them explicitly and there's the added restriction that at the very top you cannot throw an error. Like the compiler will say, hey, you have an error, you're throwing here, but nothing is handling it. You have to handle it.
Okay, so wait. Now, if I have an error in some low-level guy, I got an IO read error because your hard drive has a bad sector. The fix is I have to go up quite a few layers.
No. So there's two things. You can decide to handle it whatever way. You can decide to rethrow it.
Okay.
Explicitly, and at that point, the usual restrictions apply. Like, you cannot throw something that's not annotated in the method signature, and the signature in turn is limited to only one error type. So you won't end up with like Java, where some function theoretically can throw 15 different exceptions. And if you want to decide, hey, I just want to abort, there's a syntax for that.
Where abort means panic.
Terminate the program.
Abort means just get out of the method.
Terminate the entire program. Okay. Panic.
Yeah, I'm looking for one for the short syntax. I didn't catch it where you say, I don't handle this here. I want to just give it up to the next guy up. And
oh yeah, so in my language, if you want to handle, if you call a method that throws, you have to prefix it with a try keyword. And if you leave that just that, it will rethrow it, and all the same rules apply.
Okay, so to call anybody who throws anything, I say try. If I don't want to bother, I don't have any catchy thing afterwards. It just and now I throw the same thing that it threw.
Let me link it. It's based on the blog post from Joe Duffy.
I've seen the Joe Duffy model.
Yeah, Rust does something like that, where you just like stick a question mark at the end. That's like, this is going to give me a result. I'm going to return a result. If it doesn't make sense, just pass through.
The thing there, so in my case, there are no stack traces associated with errors by default, because that makes them cheap.
Yeah.
And the idea being there, it is, but I prefer a model where you can somehow opt in to stack traces instead of being forced to them by default and then having to try and optimize them away.
Then what you return instead of stack trace? You return
no, so by default,
one message on just one message.
No, so by default you can throw anything. You can throw a string. You can throw an integer. There is an error object. It basically just wraps a message. But the idea there is, if you want stack traces, you throw something that has a stack trace.
But you can ask for stack trace.
Well, yeah, so there is a method saying, hey, get the stack trace up until this point in time, and you can then, throw some custom error with stack trace thing.
I like Cameron's suggestion, which is somehow I make stack traces cheap by default, and then you get them.
Right. So I would say in my case, they're not. I mean, you do have to walk the stack, to get your stack frames, and the allocation could be improved. As in, currently every frame is basically, when you retrieve it at least, allocated as a 3-value array, triple basically, because my language doesn't have true tuples, and those are then wrapped on like popper. I think I called them like call frame objects or whatever. So getting the actual stack trace is not the most efficient, but the whole point there is more that we don't use it by default anyway. And because every sort of frame you explicitly have to annotate, it's actually surprisingly easy to figure out where an error came from.
Okay, that was my question. And then the question for Cameron is, how is it the case that most of your stack traces can be pre-computed and stuffed as an integer?
Yeah, I was gonna explain that. So we have a fairly unusual problem, which is we have to build a stack trace when the frames are already gone. So, I have service A calls service B, calls service D, calls service E, and somewhere along the way, any one of those calls can be async. It's the whim of the runtime, which ones are async or not. So A is already, 50 miles down the road, and B, which is running in Europe, is 32 kilometers down the road, and so on, right? So they've all, like, whatever the stack frames were that represented the information about the trace, they're long gone, which means that you actually have to, this is going to sound awful, but you have to prepare the stack trace before you go async.
Gotcha. Yep.
So if you had to do that every time, you would be absolutely dead, right? So basically you need some marker that says, hey, I've been here before, right? And if you look at, so you can analyze say a log, I've done this before, analyze a log of exceptions in a log file in a production system.
Yeah.
And what you'll find is that there are roughly 19 exceptions.
19
And-
stack traces.
Yeah, exactly. 19 stack traces,
Yeah.
19 unique stack traces. One of them happened once, one of them happened twice, one of them happened 4 times.
I get a lot of recursion where I have variable length piles in the middle.
Right. But see, that's the thing. Those are going to be so I have to do segments of stack traces. So basically I entered at this point and I'm exiting. I'm launching from this point, right? So I have to just collect that group of stack frames. And so that was the idea, is that basically you identify each of those as a number and you pass that as you go. So putting it back together is an expansion of some lookup.
Yeah, you did some lookup and pasted things together. I got that part.
So if you're using the results pattern, where you like get your results and you're like, I don't actually handle this, so I just put some syntactic sugar that says rethrow. There's only some finite number of places in your program where a result can be re-wrapped.
Rethrown or re-wraps? You didn't talk about wrapping just within. You just said, I just say I don't handle
Yeah,
it.
so I have some function where I call something that returns to me a result,
yeah,
and I myself return a result.
Yeah.
And if the thing that I called gives me an error,
yeah,
I'm going to make my object that I'm going to return as an error, and it's got a pointer to the error that was handed.
Okay, so this is a wrapping return, a wrapping result.
Yeah, so I have wrapping results as I wind back.
Yeah.
But if the thing that if I know here are all of the locations where something could wrap, essentially the only piece of information I need to add there is this is the instruction that I'm on at the time that I wrap it.
Yeah.
And even if I need to send it across the network, I can just be like, here's the binary that I'm in.
Yeah.
Here's all of the wrap points in a row.
Right.
It's very
I
sparse.
can get a really dense stack trace that I can even send across the network.
You're building a stack trace manually in user code. Every time you wrap, you're basically building a stack trace.
Right.
But it's very sparse data.
Yeah.
The wrap data is 99% the same as the data that you're wrapping, is what I think Aaron's saying.
Right. And it's basically a list in the Lisp sense of I have one integer that says this is who I am, and I have one integer that says this is who the guy I am.
Yeah. Yeah.
And I don't have to actually realize that linked list if I throw it away, and though I'll get garbage collected. And if I do need to realize it, I just walk the linked list and build the stack trace and put it.
We have a few other complexities as well, which is parts of the stack trace are invisible depending on where you catch it. So because you can't see, if it comes into your container from a parent container, you can't see the stack frames from the parent container. So those are not visible.
This is like a security issue, actually.
Yes.
Yeah, gotcha. Okay, that makes sense.
So it's an added wrinkle.
But by the way, what I was thinking about all the time, this discussion was about how cheap it is to handle the error, how cheap it is to get a stack trace. Do we want a stack trace? But I wonder whether users are more interested in how fast is the success case when there is no exception, and using results versus exceptions also have an effect on the successful code paths in terms of performance.
Yeah. So in my opinion here, you need a cost model that everyone understands. If you are making an object as your result and you're returning it, and you're actually making the object and garbage collecting it later, that will be fairly expensive. And the corrector answer is to clean the cost model is no clock cycles to 1 and just return 2 values in 2 machine registers, one which is a Boolean flag and one which is the okay value or the exception if it's not. But you don't actually need allocation when you're making it when you're making this thing.
So Go does roughly what you're describing with the the error code and the result. What Swift exceptions do, and Matt, you can probably fill in the blank on this. If I remember correctly, Swift doesn't actually have exceptions at the runtime level. In other words, it's using error codes like Go does, but it makes them look and feel to the developer like they're creating and throwing exceptions. Matt, am I on the right page? Posting the link.
He threw out a language guide error handling.
I believe this is the correct thing to do. The exception should be as thin as possible, because if you're passing huge strings, then that will become ugly quick.
I'm fine with the bytecode looking like the Go style I returned thing and I returned flag. I just want my code that if I don't check the possible error condition, I get a type error where it's like, hey, you tried to use a result as a thing. That's not a thing, that's a result. You need to unpack the result. Like, I want a type error if I didn't handle the error.
Yeah, so I think
You mean that it's wrapped? It's wrapped somehow? Oh, go ahead, York.
no, I was gonna say like the issue with like results where you results, whenever you wrap your success value, you have this problem that you have to try and optimize it away. Now, I think Rust, for example, is quite good at doing this, depending on sort of how your code is written. Like whenever you return tuples or results or whatever, it'll just compile it to like different registers. That's it. There's no actual allocation going on. But it can do that because it has LLVM and a mountain of optimizations. The model that I use at least is when there's no error thrown, the cost is a simple check. It's like a flag, we have a place where the result of every method call is written to. It's kind of like a global register 0, whatever you like to call it. And there's a separate flag that basically says whether that value was returned as usual or if it was thrown. And so after a call that could throw, it would say, hey, is that flag set to thrown? If so, rethrow, basically. Else,
how was the flag passed
business as
around?
usual. So the flag isn't necessarily passed around in calls. In my case, each lightweight process has it has basically 0 or more generators that it can run. And each generator has 2 fields called result and thrown. That result thing is, whatever it last produced, so return it through, yielded, whatever.
What I guess I'm looking for is the standard fast call path coulda, woulda, shoulda been, I got a flag passed in a register on an x86. It could be a flags register. I tested, it wasn't set. I'm done. And in particular, no allocation happened.
Right. So I don't have this implemented yet, but the idea I have is that when you call a method that can never throw, there's no overhead. Like it will just take the value.
Yeah, if you can't throw, you can compile time constant fold know that the return result is always okay and
right.
Yeah, fine.
If it does throw, it's basically there's the call instruction essentially in my bytecode, and then there's a check instruction that says, hey, did we throw? Yes, okay. But really all at that point it needs to do is pop the call frame, that's it. And then it sort of untangles itself from there. So the cost of not throwing errors is actually basically almost 0. Might as well be. The cost of throwing an error is, if there's an allocation needed for that object, that is there, and then it's basically pop the current call frame, that's it. There's no stack unwinding because that's done explicitly, so to speak.
Yeah, right. No, any of these, like the only real difference between exception throws and returning an error code is who's doing the unwind. And in the case of throwing exception, there's usually some independent piece of the runtime that's beginning to unwind frames. In the case of the error returns, you are sort of using the normal execution path to unwind your frames. But you test and unwind explicitly at each return point.
Yeah, so that there's no, I mean, let's say in the currently released version, this is all still there. But in the branch that I'm working on, there's no sort of a runtime driven unwinding. Like a throw is just write the value, set a flag, pop the frame.
Yeah, and when you say write the value, you're writing it to some shared memory location?
To this generator value, it just means someplace consistent where the caller can pull the value out of again.
Okay.
But it's the same spot as a return value. That's what I imagine. It's like a global, like a thread local so to speak.
Yeah, okay. The any reasonable compiler would be able to let you return it in a register, save you
Right.
memory traffic left and right.
The reason I have this model in particular is because I have my own scheduler, and it's completely detached from the OS call stack.
Oh, you're not optimizing across thread boundaries. You're claiming every function call or many function calls are represent a thread context switch boundary. Is that?
No, it's more like it takes the Erlang style model where everything is isolated per process, and
Okay.
more or less at any given point in time, that process may be rescheduled in favor of something else.
Yeah,
so
yeah, that's what I was trying to say there. You have a
there's this
model.
challenge where, you know, if you do method calls, you can't just in your host language sort of recurse into some function.
Yeah.
I guess you could if you save the stack, and that gets messy.
You can
and
never
lost.
be more than one instruction deep.
Right. You could do that, you know, set jump, long jump, whatever. I use Rust, and that messes Rust up really bad, so I don't. What I have my own set of data structures that represent a call frame, registers, so they're not actual registers. But there's this issue if you sort of enter a new method, how do you tell it what register it should write its result to? The old approach I had was that in the new frame, there was a field called like a return register or something.
Yeah.
And it was the register of the parent frame to write to, because each frame has its own registers. There's no limited.
It's like the Java interpreter model. Your outgoing args are put on the stack.
Yeah.
They become the input args.
And so in this
return is the last one of those for the output arg on the stack. And it's just a stack frame layout.
And I moved away from this model because it basically means that per stack frame, you have basically a word that you use for your results, which isn't a problem, but a bit redundant. It was more so when I introduced generators exclusively to make writing iterators easier. I needed to store this per generator because you can suspend and pulse them when you yield and stuff like that. And so I ended up just reusing that. So now it is sort of per generator, sort of a global, if you will, that contains the result. And so a call is, the call instruction doesn't state where the result should be written to, because it's always written to the same place.
Yeah, fine. I'm in the lower cost model version. I don't want to write my results to anywhere except a register that the return from a call knows where it's at.
I think there my setup, I think Dalvik used to do this similar, as in, at least I remember they had a move result instruction and some similar stuff, which I actually took from them. So if you call a method, it just writes the result. Then if you want to use that, there's an instruction called move result, which takes it, puts it in a register and clears it from the source.
Right.
And that's sort of how, also with exceptions, exception handling, the jumping and between like the happy path and the error path, it all reuses this same stuff.
This is your abstract execution model.
Yeah, and so the end result there is that throwing exceptions is, you know, probably as cheap as you can get it, at least in an interpreter.
Yeah, but what's the cost of not throwing an exception?
It's
storing a load of your return result.
Yeah, it's you do your call, you check, hey, is the flag true? Okay, then we have to do something. That's it.
And I would claim I don't want to play the. I'm leery of testing the flag, and I don't want to play the fetch the result out, store the result, and fetch it out of the.
Yeah, but testing a flag, I mean, I don't like the approach, but it should be free in the.
It's never free. But
hear me out.
Cheap.
Sorry, hear me out. What I meant by free is a branch predictor.
No, it's never free, and hear me out.
Well, I haven't experimented, so I'm guessing at this point.
So I've done this experiment many times. It will prevent various kinds of wide issue, so it costs you like half a clock to a clock. And specifically, you can only do a forward branch, and then you get what you're talking about of the low cost. So forward branches are predicted not taken. Because it's predicted not taken, and it was in fact not taken, It doesn't go into the branch prediction table, because if you put it in the branch prediction table, you will flood your branch predictor table with these branches that are guessed the wrong way by the no prediction hardware, but highly predictable. And then the table's no good for everybody else because the table's still drowned in these things. So you must only do forward branches for these branches that are highly predictable. Having done that, then they cost you more than you expect because they have you can only do one branch per wide issue, and they have other wide issue rules so that they stop issues. You lose a clock there. That's not zero, and it's not big if you go forward. If you go backwards, you blow out all your branch predictions everywhere. And so that in general, like if you look at the Java code for doing range checks, for doing null checks, for doing every possible thing on the planet, every one of those that I think they're highly predictable, always go forwards, even just a little ways. And you have these stupid branch around points because you have a limited forward branch range. So you stopped and you took a hard branch using a regular jump instruction. So you have a little slot that's within 128 bytes that said, now I have this, but you have to have them branches be forward if they're predictable, not taken. Same for backwards.
I'm surprised that's not the other way. Most branches are for loops, and most of the time you're doing the for loop again. I would think the default prediction would be branch backward.
That is also taken that way. If you go backwards, it is predicted to be a backwards branch. And if you successfully go backwards and you've predicted backwards, you don't pollute the branch table. So loops, backwards branches for loops want to actually be backwards and not forward to some other test and then goes backwards. You want the test that's
so it's that you are predicting branch taken by default, not that you're predicting forward or backward.
No, if the branch goes backwards, it's predicted taken. If the branch goes forwards, it's predicted not taken.
Okay, got it.
If the prediction's correct, it doesn't.
That's a reasonable default.
I'm sorry? Yeah. This is x86 came up with this years ago. It actually makes sense and works. But you have to code to it every time, and if you fail, you will flood your branch predictor table, and you won't have a branch prediction table anymore.
No, so the model at least I have, there are some alternative approaches. I briefly considered that the call instruction basically takes an extra argument, which specifies that register to jump to if it were to throw. But then you get this sort of thing again where you have to store that register in some data structure, so that if we suspend, we don't lose that value.
Oh, you have the suspend at every point, though. I would claim
so
that
theoretically, yes. In practice, it currently it will only suspend if you explicitly tell it to, or at the end of a method call.
See, I claim that Cameron's doing this the right way. That maybe you have some improvement to be done, where you let the compiler decide that at a particular point, I'm never going to context switch here under any circumstance, and then I'll get rid of all the context switch overheads and inline the hell out of it. And the only requirement is that I have context switches come around and be allowed every now and then. Yep, we lost you, Eric.
If you want to read a bunch of people debating about the should you pass in an error handler pointer, they spent a lot of time at the Algol 86 meeting.
Oh my God.
Talking about that.
Is that like you gotta?
So that's impressive, because I think Algol was 20 years old by the time Algol 86 came along.
Yeah, I believe the error handling was where a bunch of the implementations had done different things that was causing problems, and they were like, "Oh, we should actually
have a discussion." Yeah. Well, these really old papers are kind of fun because you throw away all the stuff we just assumed for so many years and realize there's a whole lot more ways to solve these problems, a lot of ways to
right. I'm so used to this, like you have to unwind the stack. The fact that there was a legitimate argument of there should just be an error handler, and if anything goes wrong, you jump to the error handler.
Yes, and now he does what he does.
And you're like, no, you have to unwind the stack.
Yeah, right. Yeah.
And it's like, well, you don't have to unwind the stack.
Yeah, you can call panic. That's definitely an option.
This is why we used to have CLI.
Yeah. Which one? Not command line interface.
No, CLI, wasn't it clear all interrupts?
Oh, the hardware instruction.
Yeah, because otherwise you'd be running along and suddenly
you had stacked pinning exceptions. Yeah. I did a little OS work way back in the day and had to deal with these things.
I don't think we've dealt with that since since the 386 though. So
I was trying to debug my OS games, the UART handler using a serial channel. I'm debugging the UART handler by typing in the debugger commands of the UART handler, and the debugger was calling a debugger, and you had to single step through the debugger and using the debugger. And, wait, code was reentrant or not? So that was a key problem though back in the day. Sort that one out.
So I had to jump out for a second. What were you going to say, Cliff, about the optimizing versus what was Cameron doing?
Oh, this is the safe point notion.
Oh yeah.
Allow a compiler to agree that it will do these context switches periodically, or be able to check for doing them periodically, but not at every small instruction or call site. So the rule for hotspot is about every 1,000 clock cycles, you'll be at a safe point, which can stop and class load or do a GC or do all kinds of things, debugger interrupts and shit like that. But you get 1,000 clock cycles worth of work where the compiler can do whatever the hell it wants.
I think York's got the interpreter though, right?
Yeah, so my model is a little different. So it's not so much that every instruction can trigger a reschedule. The way it currently works, there's a suspend instruction, but it's mostly used when you want to explicitly suspend, like if you want to wait for something. Currently, when you return from a method call, it will check how much fuel there basically is left.
Yeah. So that is a may suspend point, return from a function.
Yeah, and so that also used to be where my GC safe point was.
Yes, and hotspot has the same rule, loosened very slightly.
Right.
Which is to say, if the compiler inlines you, that return safe point goes away.
Yeah, so I have been considering sort of making this check, like, hey, do we have fuel left? No, reschedule.
Yeah.
A separate instruction so that the compiler can shuffle it around if needed. Like
yes, that is a key performance.
Right. Like the classic case will be some sort of tight loop where you can somehow determine it's not going to take up too many cycles anyway.
Right. No, DAXB loops or whatever. Yeah, hotspot does unroll and jam as a loop optimization. You unroll the loop, and then every 100 iterations you check, not every iteration.
Yeah, and so I was considering doing something similar where it would happen after method calls. It would check, and then maybe at some other points that like IO operations, things that are considered to be sort of expensive enough that the check wouldn't show up as much.
Right.
I haven't just done that because I think only 2 weeks ago did I finish my 400 compiler errors after refactoring everything.
Oh. I have to say I'm in kind of the same boat with AA right now.
Yeah, and
I changed.
So now I'm actually working on the allocator and trying to basically prove that I am both smarter and dumber than decades of garbage collection research.
Excellent.
I think there's some interesting challenges there in the sense that. Sorry, go ahead.
I was going to say, at least you got a lot of examples. It's cool to see what other people have tried.
Let's try
shoulder experience or whatever.
Yeah, and so like the challenge I had there now, and also why I've sort of postponed all this reworking of the rescheduling and such. In this sort of single ownership model that I'm working towards, fragmentation is a challenge. I mean, for a lot of short-lived applications, it doesn't matter. But for longer-lived ones, it does. And because I don't have a garbage collector, I don't have this point in time where I can sort of figure out, hey, do we have fragmentation? Do we move stuff around, etc. So I had this idea that when basically an object is deallocated, we would sort of check, are we too fragmented based on some implementation details. Then I actually have the challenge of saying, because I have thread local allocators. And you have the problem, okay, given a pointer X, how do I know which allocator it belongs to? Because the statistics for fragmentation would also have to be specific to the allocator the object belongs to.
They're not in some known address.
Yeah. Because in other words, if the object was originally allocated on thread A, but now because the process has been rescheduled, runs on thread B, and we say, oh, there's fragmentation. We shouldn't make the mistake of... Sorry, go ahead.
you're doing like OSE style threads, as opposed to
Sort
like
of.
in Cameron's model, the individual execution unit has its own heap.
They do, but so in the old model I had where there was still garbage collection, each lightweight process had its own heap, like its own physical data
Yeah,
structure.
right. Yeah.
In the new setup, because I have this single ownership model, I realized that if you want to send messages between processes, you don't actually need copying because you give up ownership.
Yeah, right. Yeah. So it's
And if you don't
highly
need
efficient.
copying,
But
you
now
don't
you're
need a
sharing
heap.
heaps.
Yeah, you don't need a heap per process. Mostly you need a heap per thread, so you can efficiently. Well, so you don't need atomics, basically.
I'm sorry. What I just said was, if you pass a message by pointer flipping and doing a single ownership flip, the object stays in the address space where it was allocated, but is
Yes.
being used by a different process.
Yes, and that's totally fine because it can't be modified concurrently.
No. Right. It's correct. Now, ask the question, garbage collection. How do I do garbage collection on a single thread?
Right. So in this case, I don't have garbage collection. I through this ownership model, it will know when this thing is done.
Right. So instead, okay. So to restate that, when
Are you
you decide you have
doing-
fragmentation, how do you detect?
Right. So the idea I had there, the heap layout is based on the MX garbage collector. I have a. Let me quickly pull up a link. I have.
Yeah, I've seen this. Yeah.
Are you doing one OS allocation per object, or you have some kind of slab allocator?
No, it's a bump allocator.
Yeah. You said
So it allocates in the original paper, I think, is like 32 kilobyte blocks. I made them 4 kilobytes, mostly because I don't want a single object to require 32 kilobytes of memory. So it's 4 kilobyte blocks. Those are divided in 128 byte lines. Those aren't data structures. That's just sort of a thing in your head. It's all aligned memory. So given a pointer, you can figure out what line it's on. And then the idea I had was that per line, we count how many live objects there are in it. And when it's 0, you can allocate into it. When it's not 0, it's in use. And so when you allocate, it will figure out the lines that are covered by that object and increment their counts by 1. And then when it deallocates, it reduces them, so the inverse. The idea I had is that when you deallocate an object, for every line that you now observe to have 0 live objects, you would increment some sort of global threat local, or what do you say, allocator local counter that says, these are the number of reusable lines. And when that counter is too big, you would just reset the bump allocation cursor to the very start of the heap. It will continue and just skip over these still in use lines, fill up the full ones, and off we go. That's basically what Imix
So
does.
for the 4K blocks, where the bottom bits in the address are all 0, you stick all those into some hash table that will tell you who the allocator is to go talk to the allocator to free it?
Well, so there's a challenge like in the old model I had with a garbage collector is fairly simple. Like a pointer couldn't cross processes, so you also knew what the allocator was that belonged to it. Now, because they can, this is more difficult challenge of, given pointer X, how do I know which data structure I need to update with these statistics?
Yes. Right. In the land of a garbage collector, he does a root walk and he knows which thread got you from the root, but you had to root walk, and then you're trying hard not to.
And so one option is
Have you read the paper on Pony's what is it, Orca garbage collector?
Ew, throw a link. I haven't looked at Pony in a while.
So essentially what I've done here is I've basically taken Imix, I threw out the garbage collector and put on single ownership on top. And you get kind of the same challenges like fragmentation. And Imix does stuff like it has histograms and statistics collecting. It's a fairly complex setup. But it can do that because it walks through the roots. It has these distinct phases where it stops things and does its business. But I didn't want to move objects. I don't want pauses. I also want the time to be bounded. So I want to know that, or basically be able to guarantee you drop an object, it's going to take this long. And not, oh, based on the size of the heap, it might take, this much longer. Yeah, that's basically what I've been stuck with, the last 2 weeks and fixing all the tests.
This is
so,
like makes the C4 Pauseless Gc algorithm look better and better.
what, the pony thing or the thing I'm doing?
No, the Azul collector.
Oh, right.
C4 Pauseless Gc.
Yeah, I thought about doing Pauseless GCs and such. For me, ultimately, like part of the reason is I wanted to get rid of garbage collection. Part of the reason also because I think single ownership fits better in the language that I'm trying to do. Like it would be no copying, for example.
Oops, we lost Aaron. I like the concept of a single ownership and deterministic free, but I also don't know what to do about fragmentation. You have the additional problems that you're pushing around from thread owners.
Yeah, so it's not so much a promise that we don't copy, as in I wouldn't make it like, say, if I were to write an ISO spec, I wouldn't say, the spec mandates no copying. It's more like, we don't really need to do it, so we don't.
Oh, I see. So this is like, okay, there's a statistical argument that says I usually don't copy, but every now and then I do defragmentation in which I copy everything.
You could do that, but that kind of clashes with the idea, like, at least I don't want pauses.
Yeah,
I don't want my app to run and it's like,
you have an issue, but you have a conflict here, which is the fragmentation will also cost you performance as well as actually cost you sort of an arbitrarily large explosion of the required amount of memory.
Yeah, no, so it is a challenge. And this is true, I think, for any non-moving collector of any kind.
Yes, it is.
The sort of current, I would say, angle I'm leaning towards is that I'll do sort of a best case effort, I think is the term. But
that's the same as every GC.
Well, in the sense, like, I'm going to do the things that are easy, but I'm not going to spend, a PhD of worth of work trying to combat fragmentation, because at least for the next 5-10 years, it's not going to matter. At least for the stuff people would use my language.
You can get sort of bizarrely large blowups if you don't.
Right, but it's more thinking like, the next 5 years, nobody's going to be writing, some big thing in it.
Maybe, yeah, fine.
If they do, I will be surprised. Put it that way.
Gil 10A has a lot of fun playing these games where he writes plain old Java code that forces defragmentation or fragmentation to hell and gone, and then he runs them on everyone's GC, and they all just follow. A little tiny Java program, doesn't do a whole lot of allocation. Any one point, amount of live memory is really small. They all explode out of memory errors left and right. Or they take 5-10 minute GC pauses on modest heaps and shit. It just wrecks them.
Yeah, so the model I have, in theory, like, you will always have fragmentation.
What is diffusion?
But the idea is that basically as objects are released, periodically it sort of resets, fills them up, resets, etc. And the balance there is trying to figure out when to do that versus how much time it might cost you to sort of find your hole to allocate into.
Yeah, okay, so this is Matt's throwing into the link. I've known this for a very long time, and I'm going, my mental models to go at it from a different direction, which I don't claim is any better, which is say give it up. For small pieces of code, be deterministically self-using the same memory over and over again, and which is what a modest pooling allocator, and for larger problems, don't bother and suck on it. And here they're claiming, no, tackle it head on. Okay, this is interesting. I'll stare at this one. I got reading out the wazoo now. Fine. Thank you, Matt.
Yeah, there's some other things. I thought about doing, what was it called again? Segmenting the heap by the object sizes.
Yeah.
But then you have this complex logic where you say, oh, if the size is this, go to this size class. If the size is that, and I was like, yeah, I'll do that when it actually matters.
Yeah, DL Malik plays the size game and works pretty well. So there are people who play the size game and it can work well.
Yeah,
and help your fragmentation.
I can see it working. In my case, I found that most of my objects are actually the same size. Like, I have a lot of them that are either 24 or 32 bytes. It's really only custom classes that can be bigger.
Oh.
But even those I'm limiting
Don't-
to.
You know, inline, like in the land of Java, people extend, and they get these giant ass objects, and then they make a bajillion
Right.
of them, and half the fields are dead. But they're not 24 or 32.
No, like my minimum size is 16 bytes. 'Cause each heap allocated object does have a header.
Yeah.
And then, you know, for class objects, so classes, it
But you're
depends on
saying
how many fields they have.
your average, if your minimum is 16 and your average is 24, you only have 8 bytes of payload for every 16 bytes of allocation, for every 16 bytes of header. Did
So
we
you
get that
lost
right?
me there. But yeah, either way, my size classes, so to speak, are fairly fixed and small.
Yeah.
And for custom classes, I just put a limit. I think it's 128 fields per class. And that's mostly so that you don't have an object that can't fit in a single 4 kilobyte block.
Yes.
I
Headers
didn't
are
want to.
overrated.
Yeah. You get complicated things now.
Yeah, because
But-
I didn't want to go down the path of, oh, we also need a large object allocator. Like, oh.
Headers
Yeah.
are overrated.
Well,
You don't have to-
header, it's literally just the pointer to the class and a reference counter. I called it header. I'm not sure if it technically is, but
Yeah.
No, I'm messing with Cliff.
Oh, I missed what you said. I didn't.
He said headers are overrated.
Oh, I see. I've certainly beat on them for a long time. Yeah, the Azul collector, we beat it down to 1 word instead of 2 on a 64 bytes.
I'm thinking for most objects, you don't need a header at all.
Bits. Yes. Well, that's the whole Java inlining thing, inline object thing. But fine, yeah.
Well,
Yeah,
until something escapes, unless it's multimorphic, why
Right.
do you need a header?
Right.
So non-escape monomorphics are all
right.
structs.
So Java's header includes a hash code, which I claim was a big mistake, and includes bits for locking, which I claim is a
Right.
big mistake. So you
And
drop
they claim that too.
right.
They agree with you.
Right. You throw out hash code, you throw out locking. Now you need a class that you can't determine at compile time. The Azul guy puts a class in because the Java model just assumes it, but it shrinks it to like 18 or 19 bits, however many unique bits for enough classes to do a reasonably gigantic Java process. Whereas if I was to do it where only the classes, I only need to count of bits according to the megamorphic class type, I probably need somewhere between 0 in most cases and 5 or 10 in other cases. And that'll just be like a fraction of a byte somewhere to be what the header is. It'll be the unique count of however many at the worst case compile point. Yeah, I see. Right. And how big's a class pointer? 32 bits?
64, just 1 word.
Yeah, okay. So in the land of Azul, the class pointer is 19 bits. Right. And if you don't hash code and you don't lock, that's mostly it. You're done. But if you have one or the other, there's a little fiddling around. If you have both, there's more fiddling around. But that's how to optimize Java headers.
No, and in theory, I could use a smaller one because all the classes are known once the bytecode is parsed.
Yeah.
And actually, the bytecode could start with the counter saying, this is the total number of classes.
Okay, you don't have a class for name issue.
Sorry, a class for
You
name?
don't have a class for name.
Class for name?
Can't invent new classes after the program began running.
No.
Okay. Yeah.
So in theory, you could make the class point like an index or something small.
Yeah, right. Put a unique. I call it a KID, a class ID, and there's a table maps class ID to a class object, and you have a class ID in the header.
That's one option. The reason I haven't done that is mostly so method calls don't have to go through extra indirection where you have to calculate sort of where in that table it is.
All right. See ya. Yeah. So the lookup requires the class ID lookup if you take a megamorphic call. If you do an inline cache, you don't need that lookup because the inline cache checks the 19 bits and then goes. So it's only on the already expensive, like the original hotspot is load, jump register. And each of the loads is indirect and can't start the next one, the last one goes. And under a modern x86, they're actually 4 clock latency to do back to back. So it's load, 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 load. 3 of them, that's 4 clock spots, 12 clocks, and then a jump interrupt would be 30 unless the branch prediction buffer gets you. So if you do them frequently, you flood the BDB buffer and the BDB does no good. If you do them rarely enough, BDB actually catches you and you're out the 12 clocks plus the BDB overhead lookup. Somewhere around 15 to 45, according to whether your BDB works. With the class ID, it turns out you need the same set. It's just a little different how the load goes. So it didn't actually cost anything. It was a scale shift on the first one to get the class ID to come out in the right bits on top of a load, load, load jump register. But that's only on the megamorphic calls, which are the rare.
Yeah, so the challenge I have here is like I have given a pointer, well, allocator basically doesn't belong to.
Yeah, that's a different problem. Yeah, I agree.
I can't stuff it in the header because then it will be bigger than the 16 bytes. Unless I make a class pointer smaller somehow. And
well, so no, so okay, hang on. So this is the other thing is that if you're doing the locking, no hash code, your thread ID was in the header because that's who owned the lock. That was the short path to get the lock on it, right? Well, how many bits do you have a thread ID? Well, how many active threads do you have?
Right.
Right.
So the thread counts I believe have limited to 256. In other words, 1 byte.
So you need, yes, there you go. 19 bits for your class ID, 8 bits for the owning thread.
And so that is one option. Although there then plays the question, what on platforms where you want to support more threads? Like
well, we
supercomputer
certainly did more than 256, but somewhere around 100,000, it gets insane on the all modern hardware, and you don't want to go there.
Right. And so I have been considering maybe bumping that to a 16 bits integer. Because I think 65,000 threads for most people should be enough.
Yeah, right.
And then I should be able to still fit it in.
Yep. And then you
there was some other data
for your class pointer under the assumption you don't have more than 65,000 classes, and you're good to go. You got it all fit in 32 bits.
No, and the thing is, there's some other data I might want to store, like these objects. They can span multiple lines.
Yeah, there's all these bits that people want to fight into the header. So the other thing, of course, you had to have some GC bits in the header.
Right. And so in my current setup, basically when it allocates, it will sort of determine how many lines does this object span.
Yeah.
Because we need to increment the counts for all.
You do a class ID to object spanning lines.
Well, so that's the thing, though. The number of lines it spans, you cannot determine that based on the class.
Yes.
It depends on where you allocate in the
right, plus or minus 1. Right.
Yeah, you can do it conservative. The original IMIX paper, they say something like, "Oh, if the object is larger than this, we just assume it's always going to span 2 lines."
Oh, this is IMIX. Yeah, I claim this is not hard to get the. And here's the offset that said it took 2 instead of 1.
No. So calculating how many lines it costs is actually fairly straightforward.
Yes.
It's a couple of bit shifts and masks, and then you're done.
Right.
So now I do the same when deallocating. So it's a bit of duplicate just to figure out how many lines do we need to decrement.
Yeah.
But I was thinking of storing that in the header because you only have the complete ones.
The runtime, I see. I did a stack allocation thing on a Zoll, and I had to know how big to deallocate as well. But maybe I got to dodge it a different way. All right. Yeah, fine.
Yeah, I haven't stored it in the header because the instructions are so, in theory, should be so straightforward. It's bit mask and bit shift, plus addition.
Yeah.
It's not the expensive ones like division and whatever.
Right.
So
Yeah. It's shuffle this, that. You get a couple clocks.
Yeah.
Registers deallocate every time.
Yeah, and I think they're given the time likely spent in running destructors. This bit shifting probably wouldn't really matter all that much.
No, the other way to look at it is the deterministic delete means that you recycle the memory much faster, which means that you get to reuse the same memory in your L1, L2 caches at the expense of having a few extra clock cycles. Like you're going to save dozens to hundreds to reuse, and you're going to pay 3 to be able to reuse to save hundreds.
Right.
So it's a huge win, and no destructors care. You don't, the unrelated destructors, you already won by 10 to 1, 40 to 1, because you did 3 clocks to save 100 later.
Right. No, so that's the thing why I'm currently trying not to stuff more than just this in the header under the argument. Like I do,
Yeah.
it kind of comes down to like in, let's say 2 years from now, I might have a legitimate reason to put something in there. But if I've already stuffed all this
Believe me, I have
metadata in
fought
there,
the header fights for more than 20 years.
yeah. So I'm basically saying no. We're gonna keep it, 60
Yeah.
bytes max. That's it.
Yeah. How to wedge in, like the other one is locks in Java. They're usually not taken. When they're taken, they're usually taken, 3 times recursively and then not more. 0, 1, 2. So you want to have a counter that goes 0, 1, 2 many. It's caveman counting. And the garbage collector guys come along, same thing. Well, I want to have a generational count. This object's been in the young gen 2 or 3 generations, and then I migrate it to old gen. So I need a couple bits. So I have a 0, 1, 2, 3 counter, and and pretty soon you run out of bits. Then you get the inflated lock header, the inflated header, which says, this isn't an actual header. This is a pointer to the actual header because it has to have a hash. It has to have a lock that's complicated. It has to have a bunch of GC bits because it's complicated. And now you have a transition where dynamically, somebody says, I take a lock, and somebody else is saying, I'm inflating the header because I want to put a hash code in it. And we're fighting with the CAS to insert the lock in the header. And complications just get ridiculous. If you can fit it in one header and don't put the hash code in, that's a big one. Don't put a lock.
Oh no, I calculate those.
Then
again.
I think you should be fine. I don't know. I say that. Of course, I know people like for stack allocation, I wanted to have what allocation site you allocated at, because I wanted to know how often that allocation site escaped the current frame or however many frames. So I was doing profiling of how often an allocation site skipped however many frames up for an escape. Like a typical factory would escape the entire depth of the factory, but then it gets to its use point, and then that's the end of it, and it dies young. And so the stack allocation say, you escaped 3 levels. So when I allocate you, I'll just put you on a frame 3 levels up, and then when that frame pops, you're done. But to do that, I had to know what your allocation site was. So I had to burn some bits in the header. And of course, there were no bits to be had, so there was another fight going on for header bits. Fine.
There was an interesting paper out of might have been the V8 group that was tracking the allocation sites by allocating an extra object ahead of your object.
That's what I did.
Yeah.
Put 1 word ahead of your object. If you were a stack allocated object only, you got 1 word ahead of you that had all your stats about where you came from and how often you escaped and shit like that.
I think they were doing it on the heap as well, though.
Yeah, I did it on the heap. Heap got big, had a lot of objects.
Yeah.
Stack on purpose was limited on how many objects you would have. You could have lots and lots that were stack local, but I immediately, at some point, I blew it out and said, I don't care. You can go on the heap. The stack was for objects that were statistically determined to mostly live young, die young. It took me a while to get that difference sorted out, and then just because otherwise I'd have huge heaps that were thread local, which sounds great, except I wanted to have a parallel concurrent background collector to collect on these huge thread local heaps. So that answer was, well, put them on the mega heap, and the main background GC just took care of it for you. So you had to only put things that were going to die young on the stack, or else you had to sort the problem of your stack got huge and you weren't prepared to deal with a giant stack heap in a single thread efficiently. It would have been nice to tell the collector that was all single threaded ownership and that he could stop the one thread and go to town and stuff like that. But the main collector was already pretty damn efficient for background collections. So give it up, go to heap. Took me the 3rd generation of the stack allocator to get that one sorted out right. All right, never mind. Well, I'm rambling and we're losing people and it's noon. Anyone want to throw anything else out here before I call it? Nope. Fine. I see a lot of glazed over 2 hours. Oh my God. It's done. Till we meet again next week.
Bye.
Bye.
Yep.